about you, Maria? You want another one?
I'm good.
You're good what?
I'm good.
You're good with what?
No problem.
Okay, why don't we do this one, okay? By the way, what's the structure of a radical? What is the structure?
Empty.
That is a tetrahedral carbon, yes?
Mm-hmm.
If I take one of those electrons away and I form a radical, is it still tetrahedral?
Yes.
It is not tetrahedral.
No.
It is.
Trigonoplanar.
That's okay if you thought it was, okay? It's okay. I am telling you, it is a pretty good guess. If you said tetrahedral, I'm not upset. It just happens that because the electron
Occupies very little space. Being tetrahedral is not so good because it just doesn't keep,
everything keeps at 109.5. If it's not tetrahedral and is what this is, what's this?
Trigonoplanar.
This is sp2 hybridized.
Yeah.
Yes?
Yep.
If it is trigonoplanar, bond angle here is 120.
120.
And because this is small, the electron goes to that p orbital.
so a carbon radical has what type of hybridization?
sp2.
And it is trigonal.
Trigonoplanar.
Because it is trigonoplanar, what does it have? It has a top
And it has a bottom.
Bottom. So they get attacked from any which way.
So, if this is doing any attack,
By the way, the electron being up here
here is the same thing as the electron being down here, okay?
So this can attack either that way or this way. If it attacks one way, or if it attacks the other way, so whenever we develop a chiral center here in our product, what is it going to be? It's going to be racemic. Okay?
Right.
It is going to be racemic. It is going to be R 50%, S 50%. Okay? So if you thought that this thing of R and S was over, you were mistaken. Now, the stability of radicals is the same as carbocation stability. Stability of radicals is the same as carbocation stability.
So the tertiary would be,
That's right. Tertiary,
Would be the most stable.
so what is hyperconjugation? Because I read that that's the reason why tertiary carbocation like is most stable because of hyperconjugation. What's that?
really?
I don't know either.
Why? What makes you think I would know?
I don't know, because you asked us that on the test.
I asked you on the test about hyperconjugation.
No, you asked us what makes it more stable and why.
Oh, okay.
I never talked about hyperconjugation. I don't know what you're talking about.
What's this radical called? This is a methyl radical. This is a primary. So methyl is like less than primary, yes? We have a primary, we have a secondary, and we have a tertiary. And here we have now a radical.
Tell me, what type of radical is this? Primary, secondary, tertiary?
Primary.
What is it?
That's a primary radical.
It's a primary radical, yes?
Yeah.
It is a primary radical that is, it has one carbon bond, but this happens to be a double bond.
Bottom, yeah.
Okay?
Yeah.
That has a special name, and the name of this is allylic.
Allylic, yeah. How many times I read that? The allylic and vinylic.
Okay? This allylic radical is resonance stabilized.
Resonance stabilized.
Can you draw the resonance stabilization for that?
Yes.
Write it.
Okay.
You do it. You do the resonance for that.
She's gonna come over there.
And that's more stabilized than a tertiary, right?
What?
When it's resonance stabilized?
Not more than a tertiary, but likely secondary. Being a primary is like a secondary.
Okay.
So here's how this is resonance stabilized, yes? What? What's gonna happen?
You're gonna move right to the other side.
What?
Is it a shift?
Okay.
One of the double bonds going to move to
Tell me, little arrow from here to where? What do I do?
double bond, put one arrow to the radical.
Like this?
Yes.
Like that?
Is it to the radical? It's
To the front.
One of them, I guess.
Like this.
Yeah.
Yeah.
Okay.
And
Like that.
like that. So one electron from here is going to go and meet this electron from here to make a double bond here. Of course, that double bond was composed of two. What's going to happen to the other one that was there?
It's gonna be single.
It's going to
Mm-hmm.
go there. And what you are going to have is this radical. The stability of this radical is like a secondary radical. Hello?
Would you say the stability of the radical is the
The
same?
stability of a allylic radical is like the stability of a secondary radical. How about this radical? What is that radical called?
Benzylic? Benzylic?
This is called a benzylic radical. And it's like the allylic radical. Now, where do you think this radical would be placed at?
What do you mean?
Yeah, is this radical, where is it placed at in here? In as far as stability is concerned, where do you think that radical would be placed?
Secondary?
Now, this radical here
Correct.
is one,
Oh, yeah.
two. It's secondary for sure.
Yeah.
But is
But
it
in
as
terms
stable
of
as a
stable-
secondary or
No.
more stable?
More stable.
More
Because of
stable
resonance?
because it has,
Resonance, right? Double bond?
because it is,
Resonance, allylic
it is
radical.
resonance stabilized, but it is because it is allylic.
Oh,
Okay.
okay.
It's not only secondary but allylic. Because it is secondary and allylic, it is as stable as a tertiary.
So it goes up one.
Yes,
Whatever it
it
is.
goes up one. Thank you, Maria, for asking.
You're welcome.
Clarified that question for everybody else. Did you get it? It goes up by one. I'm serious. It does. Right? If it's primary, it's as stable as a secondary if it's allylic. So it went up by one, right? Because primary is supposed to be here. If it's allylic, it went up by one. If it's secondary, but allylic,
Then it goes up.
it is as
Okay.
stable as a tertiary. Yes? That's what she meant to say. Outstanding idea. How about this one? It's tertiary and
Allylic.
allylic.
So that's just.
So it is
It's
more
even
stable
more stable
than
than a tertiary.
tertiary.
Yeah.
Okay?
Okay.
Very good. And benzylic is very similar to the allylic thing.
Is it allylic when it's only one carbon away, that double bond?
Yes.
So if we were like further away, would it be considered allylic?
No, it's not considered allylic. If it's like this, is that allylic? Is this
No,
allylic?
that's not because that's
This
primary.
is not allylic.
Yeah.
It is in the carbon
Next
next
to it.
to the double bond. This is 2 carbons away. This is not allylic. Okay? And if it is on the carbon that has the double bond, it's called vinylic.
Oh,
Like
so
vinyl chloride. You ever heard of that before? Polyvinyl chloride?
that's a negative.
PVC?
Yeah, PVC, polyvinyl chloride. You never heard of it? That's vinyl chloride. Vinyl because it is
And the
on the double
vanillic.
bond.
Okay.
Okay. So this is not very stable, okay? Not very good. So here is provide the major product. What's a major product?
Tertiary.
Would it go here?
No.
This is BR2, yes?
Yeah.
It's elective. Would it go here? Hello? Would it go here? Well, I mean, it does, but it would not be the major product. Major product will not go here. This is one time versus how many times for, what hydrogens are these? Primary, secondary, tertiary?
They're tertiary.
Secondary.
They secondary.
These are secondary.
Yeah.
One carbon and another carbon, not secondary, two
Yeah.
hydrogens, yes? This is secondary and this is secondary, while
Secondary.
this is
Primary.
primary. This secondary and this secondary, are they different or are they the same? They're the same. This is a CH2, CH3, but if you just look at this side, this is a CH2, CH3. They're the same. So we're just gonna focus on one. Because this is very little for primary, the major product will be secondary. How many times more? 800 times more than primary. So 800 times more, I ask you for the major, you provide only the major. What's gonna happen is the radical is going to be formed, and this is what's gonna happen. CH3 is on that side, and the CH2, CH3 is on this side, and now I have my radical like this. Yes? It can do the attack. Whoops. I messed that one up. It can do that attack, or it can do this attack on.
Here.
It's not. I have a fixation with this C. Now, once again, this is not a mechanism, this is only showing you what happens. And you could do it down here too. If it does it down here, write down what you think the product should be. What would it be? I forgot to put a hydrogen here, yes? One would be like this. If it attacks from the top, it's gonna be to the top, yes? With this towards the back, and this towards the front. Br on the top, CH3 here, H in the front, CH2, CH3 in the back. Yes or no? If it attacks from the bottom, it would be like this. It would be CH3 here. Where's the Br? Br is here because I say incoming bond. What goes on the back? What was on the back before? CH2, CH3. And what's here? BH. What are they? They are enantiomers. And not only are they enantiomers,
Racemic, yeah, they go
this is a
racemization.
racemic mixture. That means, yes, they are enantiomers, 50% R, 50% S. And you already know how to find that R and that S, yes? Do you expect for me to give you a problem on the test in which I want you to give me racemic mixture for this? Yes or no? Of course. You're going to have a problem on the test in which I'm going to give you a radical, and I expect you to tell me it is racemic if
the carbon that has developed is a chiral carbon, what would it be?
Racemic. Yeah, if it's chiral.
Okay?
Yeah.
Let's say we have this, and this is, let's say, CO2, and let's say this. What does that mean, that delta? The delta means change in temperature, and most of the time it means heat, okay? Before, when you had the CO2 and you had a double bond, what happened? The CO2 added
Yeah,
to the double bond, yes?
yeah.
And that gave you
A chlorine ion. Yeah, chlorinium. Chlorinium.
okay, chlorinium. Okay, chlorinium ion,
Yeah.
and the addition was
Anti-addition.
okay, and it gave you vicinal or geminal dihalide? Vicinal dihalide. Here, in this case, what you get is this. What was that? What happened there? Did it add to the double bond? Did not add to the double bond. This is called allylic. In this case, chlorination, yes? But let's call it allylic halogenation. And most of the time when I'm talking about halogenation, I am referring to CO2 and BR2.
BR2.
That was not the case for
Addition.
For addition, okay? Addition, they all added to the double bond before. But here, and what type of mechanism was this? Hello?
Radical.
This was a
Radical.
through a radical mechanism because this allylic radical is very stable. Okay? Provide the product.
Are these allylic halogenations only with heat, or is it heat and light as well?
You know. So what would happen here?
I just put the chlorine on the other side. Yeah. That's what you did? I know, right?
Okay.
Oh,
Yes.
okay, yeah.
Very nice. Tell me, what is the intermediate here? What do you expect the intermediate to be? What do you, guys, what's happening? You guys daydreaming? What is the intermediate here? Intermediate here will be chloronium. No. What are you talking talking about?
No, that's
It's
radical.
allylic.
Yeah, allylic.
Yes?
Okay, yeah.
This is an allylic radical, yes or no? Which, guys, yes or no?
Yes.
And this allylic radical has a resonance structure. Write the resonance structure for that allylic radical.
So those are the intermediates for that reaction.
Yes, those are the intermediates. Sophia, you have a question?
Yeah.
Okay.
Why is that one allylic?
Because whenever I give you a double bond and its radical conditions, like either CO2 and heat or CO2 and light, and you have a double bond, what you are going to have is an allylic radical because it's very stable. And you're going to have allylic halogenation. So whenever you see a double bond, you're going to put a chlorine here. Now, the chlorine is going to go there because
The
of
radical is?
because the radical is there. But it's a lie, okay? We'll get there slowly.
So in
So-
order for it to be allylic, it has to have a double bond and a radical?
Well, that hydrogen is allylic, but that is an allylic radical when it forms. And now what is this gonna give us? La Vista, what's so funny, man? How come you haven't gone to the bathroom today? Where's the double bond now for the resonance structure of this? Where? Here?
Yeah. Radical right there, yeah.
Would you like us to draw the arrows of the test?
Yes, if it's resonance structure, you have to draw those arrows, because that's what resonance structure means. So, now this radical here, can that abstract the chlorine or the bromine from somewhere, yes or no? This
Yes.
one?
Yes.
And if it does, what type of product is it going to give you? It's going to give you,
With the seal at the end?
is it going to give you that, yes or no?
Yes. Yes.
Check if you understand that.
Because it's residue, it's gonna get both.
Yeah.
Oh, okay.
Because in one case, the chlorine can go here, because that's a radical, but if it's resonating and its structure
yeah.
is this one, they can also get it from there.
I see.
Okay? This one is allylic, and this one is?
Vinylic.
No, no,
No?
no, no, no. Vinylic, no. Vinylic is on the carbon.
Oh, yeah, damn.
This is still allylic.
But you can go to the right, left side,
Which one, left side?
the radical.
Where, here?
Yes.
You cannot go there.
Why?
What do you mean? You mean, why is it going to jump from here to here?
No, I mean, if you don't put it in
Here?
at the end, you put it to the left. If it's still gonna be
No, if I put it here, it's not allylic.
no from that part.
Here?
Yes, if you put it on the left side.
Here?
Yes.
It cannot come on this side, is what I'm trying to tell you. From here, it can only go to this side, because it has to go where the double bond is. It can't go to this carbon. This is sp3 hybridized. It's not going to go there. It has to go towards the double bond. Anyway. Now tell me, which product is more stable?
Stabilized?
From those two products, which product is more stable? From what you learned in your organic chemistry class.
The one with the more, more carbon.
Secondary part.
Right in
That
the,
means
in the
the
left.
first one.
The first one?
Yes.
What's it? Tell me what this is called. I want you to tell me mono-substituted, di-substituted, tri-substituted.
Well,
Excuse
mono,
me?
sorry. Mono, but it's secondary.
What's secondary? There's no secondary double bond here. This is called mono-substituted. The double bond has one substitution on it. And this one is di-substituted.
Because that double bond has two different groups.
The double bond has one and two carbons on it. So that's di-substituted.
Oh, okay, so not the double one.
Which one is more stable? Di-substituted. Because this is more stable, it is the major product.
And that's what, it's the minor product?
So that is a major product, and it is a major product not because of the allylic radical. It is the major product because of stability of the product. Okay? This is a major product, not this. It's not what you expected. Yes, you expected allylic, yes? But the allylic, if it has a resonance structure and it can go to a more stable double bond, it will. And that's the major product. Yes or no?
Some stained on the.
Thinking about leaving?
Oh, I'm coming.
It is one jump away, but that's a carbon. This carbon is this carbon.
Oh, see, I was thinking it was on top, like, above it. Above it? Yeah, I thought that's where it started.
No, this is a CL, that's the bond.
Oh, so you have to start with a carbon. Oh, okay.
Guys, look, how many carbons here? Let's count to see
One.
if I did it right. 1,
2, 3, 4, 5, 6.
The answer, this is not elongation of any carbon chain. The answer is going to have 1, 2, 3, 4, 5, and 6. Yes or no? The double bond used to be here. It's not here anymore because once you form the allylic radical here, by resonance stabilization, the radical went here. And that's when it picked up this chlorine. Okay? Yes? This same reaction can be performed using something called NBS. And NBS is N-bromosuccinimide. So let's say NBS is N-bromosuccinimide. Sucks, yeah. That's called NBS, okay? N-bromo, because the bond is on N, on the nitrogen, bromo. The bromo is on the nitrogen. Succinimide. Who cares about the spelling? Yes, it's not a spelling bee. So, what that is going to do is, this is like a source of bromine radicals. Okay? So, this is like a source of bromine radicals. And if you have that double bond and a bromine radical, what is it going to do? Allylic bromination. So provide the product. Guys, who has the course schedule? Get that, Mitch. What day is today? The what?
26.
Of what, of May? You're behind schedule, my friends, yes? We got like 6 chapters to cover in 2 weeks. What? What's so strange? It's just studying.
What is this going to give us? You. Huh? You're 10. You must have gone to the beach with my book. Right? I don't know what you were doing at the beach. If I catch you at the beach, I'm gonna start looking for you at every beach. All right. So, what are we going to have?
Radical.
Hello.
Yeah, with a BR right there. BR. Yeah, BR.
You sure?
Yeah, I'm sure about that one.
Okay. The resonance one is which one?
It's gonna go on the
Double bond with a B.
The double bond used to be here.
Yes,
Resonance
right
is
there.
gonna go here, and the
And
CL.
the BR gonna go right there.
Oh, the
You're
BR.
asphyxiated with that.
Yeah, I have a fixation for, I don't know for what reason. Which one is the major product?
Yeah.
The one on right.
This is the major product because
It's disubstituted.
It's the
More stable
double bond.
bond.
Did we talk about Sisef rule here before?
Sisev.
Sisef?
With a Z?
Z. Site.
Is that
Psych.
Russian?
it
Now
is
that-
Russian.
These Russians.
That's all chemistry is about, huh? Bunch of old Russian guys.
Okay, write it down. Sisef rule says,
Is that like kind of anti?
like antimicronica, but Sisef rule says that the more stable double bond is the one that is formed. Did you get that, Luis?
No.
More stable double bond.
Wait, what? Can you repeat, sir?
No. Haz la viste.
La vista, what was it?
La vista. I forgot it was like. Okay, guys.
What was it? Can you repeat?
I forgot what I said.
You say repeat, so.
Guys, don't worry. We will go to Sisef rule again, okay? Don't worry. We'll come back to it when we do eliminations. Should I talk about Hammond's postulate?
We just mentioned it.
Yeah, but more. One more? I don't want to waste too much time. Write this down. Hammond's postulate.
Hammond's postulate.
Do you know how to spell Hammond's?
HAMMONDS.
Hammond's.
Postulate. POSTULATE.
Oh snap, I broke somebody's phone.
It's a girl's phone. Whose phone is this?
You know.
Whose is it? Is yours?
Same color as your shirt.
Hammond's postulate says.
Jesus.
What happened? She did it?
Yeah, don't worry. It's alright.
Careful of
We're sitting Sophia there next time because she takes care of stuff.
Hammond's postulate says. That an exothermic reaction
In an exothermic reaction, the transition state looks like the reactants. For an endothermic reaction, the transition state looks like
The product.
the products.
Okay, so it's exothermic, transition state like
Reactants.
reactants, endothermic, transition state like products. You want to go into there is something else in the book. Oh yeah, let's do this one. Damn, I forgot.
Man,
I'm tired. Hungry.
I'm good. Study. So much things to do.
So HBr to a double bond, what is it going to give you?
BR is gonna
H and BR.
An alkyl halide. And
Yeah.
what about it? Where is the hydrogen and the bromine going to go?
Yeah, the first one is Markovnikov addition,
Outstanding.
but the second one is anti because of the peroxides.
Now the bromine is gonna go here, because that was the more stable what? Carbocation.
Carbocation.
If this has stereochemistry, meaning that if this center is chiral, what is it going to be?
No. Do it. Do it. Do it. What the?
If the carbon is chiral, it's a lid. Outstanding. All right. If the carbon is chiral, it will be racemic.
Racemic. 50%
So, now
R,
here-
50% S.
Before, every time you use a peroxide, it will give you anti-Markovnikov. You remember when we did hydroboration?
Yes.
The oxidation step had hydrogen peroxide, yes?
Yep.
So I didn't tell you then, but peroxides, when you use peroxides, it changes the mechanism. And what it does is it gives you anti-Markovnikov. So this is Markovnikov without peroxides. And this, what is the product here with the peroxide? Anti-Markovnikov.
Bromine is on the right.
Where does it go?
The bromine is on the right. Yeah, right there.
And this is anti-Markovnikov. With peroxides. Yes? Should we start SN1, SN2?
Oh no, Professor.
No?
Please, no. Some of us have been here since 8
Sophia,
o'clock.
what do you say? No?
We're saturated.
Why?
We already went over it in lab.
We went over in lab, but we need to go over it here. Now we have to go faster next week. You like it fast? How about you, Maria?
Wait up,
You're
this
giving
is,
me a silent treatment?
This is chapter 5 in the Klein book, right? SN1,
Alright.
SN2.
So,
I think
yeah.
it's chapter 5.
Let's talk